excited that Ido is here. Meeting is being streamed live now. Okay. Ido Kaminer from Technion. He did actually his PhD in Technion with Moti Segev, and then he did a postdoc at MIT as a fellowship, but working with Marin Soljacic and John Joannopoulos. So what I like about Ido's work is very creative and very interesting, different directions. In particular, one of the works that he did a while back when he was at MIT was this shrinking light and looking at interesting effects at light-matter interaction. So I am very curious what you have for us today, and thank you very much for coming. Yes, I give you the.
Yes, it's the best to do this, to connect it somehow.
Thanks. Yep.
Let's try it this way. Tell me if you raise a flag if there is something not working well, but I think it looks good. Thank you very much for the invitation and for the chance to come and meet people. I'm looking forward to more meetings and exciting ideas. And I think I'm glad for the interest and already the morning meetings that kind of started us with some adrenaline and interest. And I want to take you on a small science journey with some ideas that all resolve around this creature, the electron. And let's see how well the pointer works. Okay. Well, yeah, but we'll manage it, I think. So my lab is doing both theory and experiments in different areas, but much of what we were doing recently has to do with the free electron. The electron, the fundamental one, the one from QED, right? The one that moves in free space and can be relativistic, and going into areas where quantum aspects of the electron interactions play a role. So I want to take you on a journey of the kind of interesting physics we can do with it, with the electron, with this very fundamental creature. And many of the experiments you will see are done in electron microscopes. And this is an example of how what we call a transmission electron microscope, or a TEM, looks like. And that's those electrons reach to about 70% the speed of light. And in recent years, they are also showing more and more quantum phenomena. And I think that's a fun game that we have something that's is a little bit relativistic, but is also a little bit, and more than a little recently, quantum. And the other thing about it is that we modify it heavily. We put a lot of laser light into it, and that's probably by now the most heavily modified electron microscope in the world. And it's getting more and more bizarre, and the kind of things we do to it to do those experiments are getting more and more complicated. So I'll take maybe 2 more slides to talk about the electron as a kind of fundamental creature and why I like doing physics with it. And I think the most important thing to remember is that it's very old science. And it's very old in the sense that when you heat up your food in a microwave oven, you use free electron radiation. And then there are antennas based on free electron radiation, and it's in synchrotrons and free electron lasers. So it's I think a worthy question to ask, why are we back to play with that thing after so many years? And still, there is something that happened in the community in the last 10, 15 years that got a lot of people to be interested again in that old creature. And it's because both theoretical ideas that came from quantum optics and from new tools in quantum optics kind of brought us back to ask different questions about what's the fundamental nature of free electron radiation. This thing that we know for so many years is actually not as simple as we thought for a long time. And that allows us to do new stuff with the electron. And I think the other thing that's important is the electron experiments that we can do now were not available in the, let's say, the Soviet era that did a lot of the famous important experiments with free electrons in the past. And for those reasons, we see interesting things happening. So let me show you 3 examples of the type of physics that we can do with free electrons that makes me interested especially. One is in radiation sources. Here's one idea that goes into materials. We took van der Waals materials. Van der Waals materials are perfectly periodic. You can send electrons through them. And by doing that, sending the electron through the material, it's modulating the electron trajectory and causing the electron to also induce dipoles to oscillate in the material. And you can think about it like an antenna array. There is a periodic structure shaken by the electron, and then the radiation you'll get corresponds to the internal periodicity inside. And what we get is X-ray radiation, and that's probably the only accessible tunable X-ray source you can put in a compact lab these days, unlike synchrotrons and very complex facilities that reach to those scales. In another aspect of electron physics, not the radiation side, but maybe even more famous, is electron microscopy. Right, if we see COVID, those images are typically coming from electron microscopes. But what do we do with electron microscopes these days is we look not at the matter, but at light. We use the electron microscope resolution to image light states in very small dimensions. Those are examples of Bloch modes of light. Those are photonic crystals. And we can see the Bloch modes in the photonic crystal and how it behaves. We also took that to 2D materials. And I'll show you a little bit more about this later. But this is an example of a wave packet that's propagating in hexagonal boron nitride. It's a wave packet of 4 non-polaritons that propagate from the edge of the material towards its center. And we can create movies of the motion on sub-micron resolution, and actually few nanometer resolution in some cases, and see the dynamics of light wave packets or combined light matter wave packets in those cases. Now, the side I like the most about electron experiments and what we can do with that is actually the third example I'll bring here. And that's the idea of acting back on the electron. We can take the electron now as the thing we want to operate on and shape the electron's wave packets. And free electron wave packets are those Schrödinger creatures that we can really manipulate and shape. And for example, this is an example of experimental data we are collecting in the energy domain. So what you're seeing here on the what you're seeing here on the x-axis is energy loss, or basically what we're seeing here, the electron energy spectrum. And that the idea behind this is that we can measure the single electron energy and how it behaves, and repeat this experiment many times. And then we get this histogram of electron hits. And what you see basically is that the electron is not a single energy, but is a comb or a superposition of many individual energy peaks that are exactly separated by h bar omega. So the laser that shapes it makes the electron, like we know in optics, in frequency combs, right? We have a photon that can take many frequencies. So here the electron is a superposition of, in this case, tens, but we can get to a few thousand individual energy levels separated by the photon energy. And that electron comb is one example of how we can shape, and it's a single electron that takes this kind of state. And that, I think, is a wonderful thing that we can really manipulate the wave functions of electrons, and we'll discuss how this alters things down the road. And finally, if I have time at the end, I'll mention it a bit more. We were doing experiments where we take quantum light or light with photon statistics that's not classical, and we shine that on the electron. And then we do experiments where the light interacts with the quantum nature of light and then imprint the photon statistics on the electron. So again, we can take from the electron wave function quite a lot about the light it senses. Okay, so now a step back about how we understand electron interactions. And I want to take you for kind of high school level physics for a moment. So if we have an electron that passes through a laser field, or generally any electromagnetic field, it will be described by some type of electric and magnetic field in space and time. And we can ask, what will be the electron kinetic energy after the interaction? Let's say it started with some E0 kinetic energy. What will be the change in kinetic energy after? But how would you approach a problem like that? Like, what's the right way to find delta E, given that you know the exact electromagnetic field in space and time? Right? What's the typical high school physics answer for that? Right? You want to find the potential, but how do you find that from E and B? Right? So not just the potential, right, but we imagine the electron somehow moving inside the field, right? And when it's exiting the field, it has
you want to integrate E over the path, right? The electric field over the path.
Exactly. We want to integrate the electric field over the path. So, and that means in a sense, but what's happening at every instant in time, right? You can start from thinking about the electron having some force acting on it, right? And then we integrate over that force to find the energy change, right? So I'm not trying to ask any tricky question. well, at least for now. But the answer, like the Lorentz force, is the simplest thing you would expect, right? There is an electric field acting on it, and actually there is also the V cross B term added to it. So that's the force acting on the electron instantaneously, and then you integrate on that force along the path, and you get the total energy that the electron will get. And if that was indeed enough, then we would expect the experiment to look something like this. There is an electron energy distribution concentrated around E0, and it's pretty narrow. So we can think about it as almost monoenergetic. And then we act on it with the electric field, and we would expect that to shift by some amount. It can accelerate or decelerate actually as well, right? So that will be what we expect. But what we actually see in experiments is something like that. Okay, and seeing this really got me interested in this field. And I actually saw this for the first time in January 2015. It was in Nanometa in conference in Austria. The Roppers group from Göttingen, Klaus Roppers, presented that, and that really got me interested in the field, and eventually also to ask places where I interviewed to build this kind of setup and to go in this direction. So some conferences can be very important, even a single talk. And in this case, why is this exciting? I think there are two aspects about it that are pretty interesting. One is that the field is not a single value anymore. There are multiple options, and that's a very good mark of quantum. But maybe more than that, there are individual peaks, and they are separated by h bar omega. Right? There is h bar in there already, and that h bar omega is the energy of the photon. The electron actually performs something like absorption and emission, and you can actually show that this is stimulated absorption and stimulated emission of individual photons from the laser field, right? And then hopping left and right. And you can actually exactly model this as a quantum walk. But before we go all the way quantum, it's also worth saying that this was not the first place where it was observed. The first place was in 2009 in Caltech by Ahmed Zewail. And then it was a mystery for a little bit, and then there were theory works coming out. This is Ana Sancho Garcia, and also Javier Garcia de Abajo and Matthew Koziak explained that a year after. So how do we really model this type of results? Right, it's no Lorentz won't be enough, Lorentz force, right? We need h bar from somewhere. So what do we do to model this? And nowadays, I feel like people are more in talks I give are finding the answer here easier than the left one. Says something about education, I guess. So we need the Schrödinger equation for that. And it's actually the free space Schrödinger equation for the electron, where we add in the vector potential and the scalar potential, depends on the gauge, into which we stick the fields, right? So in solving this PDE, partial differential equation, we can solve everything. And actually with some approximations, like the electron is relatively energetic and paraxial, you can simplify that and even do everything analytical. So nowadays we can model things like this piece of data to match it with a theory precisely. Okay.
Going back to high school physics, energy and momentum conservation. How much I can juice energy and momentum conservation to understand this?
From how much I can understand this from energy and momentum, I guess there are kind of two pictures we like, right? One is saying, okay, the electron just absorbs a photon or emits a photon, and that will cause it to shift right and left. So that will be real conservation of energy. It will take it from the field. But this is one story. The other story is Schrödinger equation. And what do we do to Schrödinger? We put a field that is periodic in time. So we think about it like a Floquet system, or periodic in time. We can convert everything to a Fourier series and solve for the coefficients. And somewhere in this Fourier decomposition, you will also find the energy conservation hiding. Right? But those two kinds of pictures are actually equivalent, even though it's not so easy to see conservation of energy in the Schrödinger equation, I guess. So I don't have an intuitive picture for the top theory, but we do think about it like the electron hopping right and left.
But the phase mapping will tell you where the light is coming out.
Phase matching in the sense that, yes, so you can say what, where the light is coming in, what angle it will go out in a.
So various peaks will go off in different directions.
They could. It's normally not a very strong effect. you would expect basically not just conservation of energy, but also momentum, right? And the momentum will potentially push the electron sideways. And so there are a few experiments powered by us that show that the electron actually is pushed sideways. Whenever it absorbs a photon, if that photon moves sideways especially, right, the momentum will push it to the sides. This was first shown in collaboration with Fabrizio Carbone. It was Nature Com 2018. So that exists. It's normally not a very strong effect because the electron is so strongly paraxial that a tiny shift in momentum to the sides won't change to it so much. But yeah.
The outgoing photon.
Yeah, I mean, full conservation is this. Yeah, you take this into account and you still find those small shifts. Yeah, but it's but generally this very basic picture is the way to fully understand it for me, and the difference between the Schrödinger and the Lorentz is to think about this picture on the top right. The electron wave function here is important, right? And if on the left side we imagine an electron as a point particle in its interactions with light, what we actually need to do, and that's what happens in real experiments, is that our electrons are actually wave packets that are big enough to be much larger than the wavelength. So the electrons extend over a scale that is many, many wavelengths, actually so big that we can consider it as a plane wave for solving this in practice, and it fits very well with experiments. So it's actually many times larger than the wavelength of light. And in a sense, that's the reason why the wave nature matters. So in everything that comes next, the way we use electrons for experiments is we treat them as plane waves. We treat them as large waves. And that's quite important. And it makes me wonder, actually, looking back into 100 years of electron physics, where was this all along? You look back at the synchrotrons and free electron lasers, and maybe the microwave oven, and wonder where the electron wave nature, what was its role? So this is a kind of part of the research we're doing is looking back and asking those kind of questions. And we have, for example, from a year ago, the first experiment asking how electron acceleration is modified by the fact that the laser acts on it. And that's experiments that show that there are some variations and there are places to understand where quantum classical correspondence comes back. So I believe we now understand this picture, but we still have things to wonder whether we can, for example, optimize old devices and systems by considering that aspect as well. And I think it's an interesting question. There are other groups you can read interesting work by Peter Baum and by Avi Gover on those aspects that are looking into this, both in theory and experiments. So with this introduction, what I want to do next is to show you how the experiment we're doing, what's behind the scenes. So I'll show you an experiment to get a feeling.
Can I ask a question?
Yeah, definitely.
Yeah, this is Bill Phillips on Zoom. I'd like to follow up a little bit on Alan's question about phase matching. Usually when I think about phase matching, I think about the some kind of an extended medium, but I get the impression from what you're telling us that this is basically a single electron effect. That is, has to do with the wave nature of the electron, but it doesn't necessarily have to do with the collective aspect of the electron's motion. Is that true?
Yeah, so first, the experiments that we're doing here are happening on the single electron level,
right?
Either because there is just a single electron per pulse, or because the interaction between electrons is negligible.
Great.
This is very different from most of, from the microwave oven, if you like. And then you can ask how many of those things will extend when many electrons are acting together. And there are a few results on this, but not so many yet. But that's an interesting question, right? To what extent many electrons will collapse each other and will go back acting as point particles versus will have a joint wave function and will do something even more quantum.
But this is mainly a single electron effect. So then what I'm wondering is phase matching really the right way to think about momentum conservation, or is it happening at a more elementary level? Maybe Alan could chime in here too.
Yeah.
I think I'm wondering about, you've got a width of these peaks here.
Yeah.
And if I would just kind of ignorantly guess, I would say the width must have something to do with the extent of the electron wave function, because that's acting kind of like a grating in the motif.
Yeah. So I would put the phase matching aside for a moment because it can be mentioned in many contexts, and I'll even use it later on. Maybe we'll go back to this. I'll have a point where we actually use phase matching to increase the interaction strength. But let's think about the widths of the peaks. That's something we see experimentally. The easiest way for me to think about it is as uncertainty principle, right? The widths of the peaks here will typically be related to the initial one at the beginning before interaction, right? And that you would expect with uncertainty between energy delta E delta T being h bar be related to the duration of the wave function. So it's actually it's correct to about 2 orders of magnitude, and there is a big debate of why it's so far away. And there is probably a mixture of density matrix description and not just pure uncertainty. And there are still debates about this, about where is the actual limit of that.
And then just a backup question. I never actually said that the wavelength of light, or the light that's interacting with, is at omega.
It is what? Is
the frequency of the light that you're interacting with is the omega. Yeah,
the omega that I have in there, and maybe I should have said, is the omega that's the frequency of light. Yeah, and it's since we do it in optics, but and more recently in infrared, it's on the scale of few eV to fractions of eV, but typically, and we're lucky to have electrons that are monoenergetic enough to be narrower than that. So we can see individual photons being absorbed and emitted. That's not an obvious thing, and it's thanks to technology that's really made a big leap in electron quality. Okay, so I'll show you a bit of how this kind of experiment looks like, and I think this is a nice demonstration of what's happening. And what we're going to do now is use the electron nature and its interaction with light to create a microscope that looks at light. Okay, and that's the idea of what's running here. Let's see that it's starting. Yes. Okay. So the basic idea is that laser pulses that are exciting some material, and this is in this case hexagonal boron nitride, for example, so wave packets propagating inside, will creating these dynamics with some space and time behavior that we would like to image. So what we do is we split our laser pulse and we create electrons so they arrive right in time to interact with that wave packets in the structure. And now the idea is that the electrons that interact with the wave packets, some of them in this picture will be accelerated by the laser field in the material, and some of them will not be. And then what we do is we filter out the electrons, only capturing the ones that interacted, that got affected by the field. And that allows us to capture only the right electrons and create an image of the field, because only those electrons pass through the field in the right time. Now I'll pass through this again, but the idea is that we repeat this experiment multiple times with different delays. So the electrons capture this phenomenon every time at a different time and different point in time. And then what it looks like is basically a movie of many frames. And this is the raw data. That's exactly how the dynamics of wave packets inside a phonon polariton material will look like. And I'll start this again from the start because it's a bit easier to understand in second time probably. So we have a laser pulse now coming to the material. We're actually changing the color to match it to a resonance in the material, and we create those wave packets. Phonon polariton wave packets in HBN, it's a beautiful thing. Now we split the laser, right? You see now is we split the laser pulse, we convert it to a fourth harmonic. What creates the electron is the photoelectric effect, laser light hitting a tip. And those electrons, they look like many, but in reality, it's one that it's actually hitting. Part of the electron is interacting with the field and part of it isn't. Now, when it's interacting with the field, it changes velocity. And the reason this is going 90 degrees at the bottom right is that this is a spectrometer for electrons. It's turning by a magnetic field, like in high school physics. And now the faster electrons will be the ones we collect. They will be going through some slit that only captures those, and then through a bunch of more magnetic lenses to create those movies. And then we change the location of the mirrors. We see them shifting in there, because we want to delay the laser light arrival. So the essence of this, anyone that knows pump probe spectroscopy and pump probe microscopy, those will be exactly the same techniques we use here, except that the probe is an electron. And that's what makes it possible to image things on very, very good resolution in space, but also with other aspects that benefit from the electron dynamics. Okay, so that's the basic idea with this type of thing. And now, as a brief historical overview, this entire field, we call this photon-induced near-field electron microscopy. This is right at the top, or PNEM. And that's basically the idea of using electron microscopy to image near fields. Okay, and that was coined by Ahmed Zewail in this Nature paper from 2009. The original measurement was on carbon nanotubes, and you can see the field around the carbon nanotube being imaged by the electron. It was a riddle at the time. The theory came a year after, and that was done back then in parallel by Javier Garcia de Abajos and the group there, and also by Sainte Park from Caltech. And then it took a couple of years for other groups to join on, and this is the first work to follow up on it was standing wave plasmons in silver nanowires. This is from EPFL, Fabrizio Carbone, and there are since then many others join in, and there are more microscopes of this type being built around the world. But I'll say that the place where I joined the field was in 2020. This is the first experiment we showed in the context of PNEM. It was a back-to-back work eventually with the Roper's group, where what we showed here is the first time how electron interacts with cavity modes, with light trapped in materials where the light itself holds there for a while. Then we can not just measure the shape of the light field, but also the dynamics of the light field. And for example, here, measure for each angle of coupling and wavelength, we can reconstruct the entire band structure, the photonic band structure there. The group in Göttingen was looking into whispering gallery modes. And in both cases, we could measure the lifetime of each mode as a function of coupling angle and frequency. And then it led us to think where next. And I think the most recent step in this field is this work where we took the entire field into two-dimensional materials, and we started looking into the dynamics of wave packets created into the materials. And you can see here two examples of the same flake of hexagonal boron nitride excited in two different conditions. That all we change is the wavelength of light. And what we do is we hit different types of modes on the dispersion of those wave packets that propagate through the hexagonal boron nitride. And what I find really nice about the bottom part is that you see that the wave packet actually splits to two. We bring one pulse, and it actually creates two wave packets moving inside. It was pretty peculiar for us at the beginning, but theory is always very easy when you know what you need to get. It's always easier in retrospect. So we can show that hexagonal boron nitride has this hyperbolic band structure. It means that there are multiple bands inside, and they have different group velocities. So we can actually excite multiple modes, and then they will split apart and move apart from one another. To get to this regime, we had to do a pretty tough effort. This is partially getting very good samples and working together. This is ICFO, Frank Coppens, and from Orsay in France, this is Mathieu Koziak. In Kansas, they make those, this is the Edgar group. They make isotopically pure hexagonal boron nitride materials. It also means we had to take the entire technique to the mid-infrared, and that opened up a lot of interesting science that I'm still looking for. What's the right and most interesting things to do with this? And that's a lot of thanks to the work of Yaniv Kurman from my lab that just graduated, and Rafael Dehan, who is our chief experimentalist. And now what's happening now, where the frontier is one step beyond this, because we have this ability to look at the full spatial temporal dynamics of fields on the nanoscale. So we wanted to know what type of things we could look at that we will not be able to see directly otherwise. And here is an example of what this can enable, and this is still in review, but the basic idea is that we take a flake of still HBN, different excitation conditions, different flake, and we can see this dancing dynamics of the field. And I think something beautiful about it is that, it looks completely random, but after you understand what's happening inside, you can actually learn a lot from seeing the full dynamics there. So you can see the field starts from the edges and then propagates inside to the inside. And then here is an interesting idea. What Yaniv did, he tracked the locations of the zeros, the place where there is no field at all with image processing. And then by following those dots, you can see something interesting. There are actually two types of dots. The red and the blue are ones he actually colored manually. There is only one way to color it, a bit like Sudoku. And the idea is that if you know what happens to fields at exactly point of zero amplitude, and why those points of zero amplitude are so robust, right? They don't disappear. They move around, but they don't disappear, even though the field is continuous. So you would expect roughly some, to smoothen out. right? If it was liquid motion, you wouldn't expect points of zero amplitude to exist so easily. And I'm sure some people here are familiar with this because I know there are groups here working on aspects like orbital angular momentum and vortices, because that's exactly the physics that we see in this dancing scenario. And the idea is that if you think about the phase of the field, and that's something that we don't see here directly, but we can follow by looking at the zeros, you know that the phase of the field has to be continuous, and any closed trajectory will do. We'll always have to finish up by either the same phase or a change in 2 pi, 4 pi, minus 2 pi, minus 4 pi, right? So what happens basically is you can characterize every point, every circle like this by an integer number, which is the multiple of 2 pi.
What's the physical observable?
The physical observable that the electron itself sees is the integral of the field along the trajectory, right? Which is typically dominated by electric field contribution. The magnetic field does almost nothing. So it's the integral of the electric field along the trajectory, which is practically seeing, you can say, the modulus square of the complex phasor of the out of plane field, right? And that's close to intensity. If we want something close in like, it's not exactly the intensity because it's integrating along, it's including the field inside, but it's, yeah.
They go just over the thickness of this layer.
Yes, and there is some field pointing up and down, and we basically see the out of plane field in this, right? And that allows us to see intensity roughly, right? Not exactly because it's the E field only and not the B field, but we can reconstruct the rest, understanding that we know the mode shape and how it behaves with those kinds of modes, with polaritons. And then I think the beautiful thing is that from theory, we know how to say that the phase itself has to wind around those points. And since it's continuous, every time that the number is not zero, 2 pi or minus 2 pi, there has to be a point in the middle from continuity where the phase is not defined. And those points are ones with zero amplitude necessarily. So that's what we call vortices, right? Or of phase singularities. Yeah.
So your picture is an intensity heat map, sort of like that.
Yeah, you can think about it like intensity heat maps. It's to a good approximation, yeah.
But you don't really have any phase expression there to really classify it as a vortex or an anti-vortex sort of pair. So how do you really color the dots?
So if we had a way to image the phase, and we're working on this, and I hope we'll be able to show this as well, then it will be obvious, right? You'll be seeing the face. That will be beautiful. And with other tools these days, like near-field optical tips scanning, you could get there. The tips will deform the field, and not show you dynamics as easily, right? Here to get phase is a long story, not for now, but for now, how do we get it? How do you do the coloring? You follow the dynamics. You have the entire movie, and you ask yourself, what pairs of points, when they meet, will annihilate? Those have to be opposites, right? And which ones will repel? Those have to be the same number. And if you do that, you'll find that there is only one way to color it, up to flipping everything by minus, right? And that's so the Sudoku has only one solution here.
So is it also because you have these empty spaces, zero amplitude, that aren't disappearing for
They're pretty
a while?
right. They're pretty stable. Yeah.
So even with in the absence of the phase information, you kind of,
Yes.
I mean, are there any other alternative explanations?
But for many other samples,
You get the phase information and
yeah,
it isn't what you say, they aren't vortices.
right.
Are there any alternatives?
That will be explaining this with not as vortices, basically. I don't know ones, and I think we didn't, in a sense, for many people here working with 2D materials, with polaritons, with older style plasmons as well, it's kind of obvious, right? We know this dynamics, it's Maxwell's equations for long enough. We know this is supposed to happen, and we are just really happy that we can see it actually in motion, right? We can see those points annihilating, for example. The creation and annihilation of vortices is something that we have not seen before in movies like this, but we do expect this type of physics to occur. But there, by the way, there are other samples where we do not know how to solve the Sudoku, and for them we will need the full phase, right? It's not always so easy to follow. It depends on the shape of the boundary conditions.
The question is that what's the alternative? For example, if you have a whispering gallery, like,
yeah,
the phase in the middle of the disk, it's zero.
It's zero, yeah, and it's kind of degenerate zero, large zero.
And into the minus IK.
Right.
And there is no vortex.
Right.
What you were saying actually was intriguing because we have access to dynamics. So I can think of some Kramers-Kronig business that I have the intensity, I might be able to also extract it ways if I have access to time.
Yeah, is it giving us enough information in a... One thing we could try is if you can play on the following. If you only know the points, the colors of all the points, and now you remove all the rest of the information, you can actually find where you will see peaks in the field and where you will see those kind of valleys. So the locations of the points and the colors will give you the ability to reconstruct the entire field. So there is something like Kramers-Kronig in there. I feel like, but I was kind of doing the opposite, right? I started from the points and I got the field intensity. You're asking, can we go from the intensity part and can we get the phases? I think that you will not be, for a single picture, you will not be able to. But I think that for a movie where you see them annihilating and creating, then you will. And then if the movie is long enough, it becomes important, right? If it's not long enough, you'll not be. But I don't know for a fact, like if we can prove a relation like Kramers-Kronig. Anyway, this shows the kind of capability we have, and we're thinking now, and it will be wonderful to discuss it today and tomorrow on like whether we can find other systems where we have this capability gives us an advantage. It's worth pursuing. But one part of what we're developing these days is thinking beyond this, because this is still Maxwell's in the most fundamental sense, and we want to go a step beyond. So I want to show you what we are developing these days and what part of what the community is thinking about. Because so far, the major papers that came from experiments with our system, with the ultrafast electron microscope, looked at the flow of light. But part of the interesting physics is hiding in the charges. We want to see the motion of charges. And that's something that has been promoted by different people, including Ahmed Zewail, before he passed away. There is a YouTube talk he gave in 2015, where he was talking about the vision of could we see transport, could we see electron motion in condensed matter physics. And I think that's an important goal. It's a very big goal. It's bigger than the field of optics in many ways. And there are many reasons for liking to do that. You can think about your own, but I will give 3 as examples. We want to see hot carriers. We want to see the dynamics of photoelectrons. We want to be able to look at topological materials. They're famous for those electrons that can only go one way for a certain spin. Right? Can we see that? Can we actually have a microscope that will look at that? I think that will be wonderful. And then another example in nonlinear optics. A lot of nonlinear optics is dominated by the motion of electrons and holes in matter. And those are 3 examples. There are others. Of course, there are many groups and many methods that are trying to get this kind of knowledge. And there are already a lot of things to describe, and it could be a full talk about point projection electron microscopy and photoemission electron microscopy in particular, are approaches that use electrons in different ways. So far, very limited. For example, limited by resolution in space and time, and also in being able to mostly see the surface, or we actually want to see the dynamics in bulks as well. So we were thinking, can we develop a method that will use our electrons to extract the dynamics of electrons inside? And I want to propose an idea that I think is really nice. How a scenario where we have dynamics of charge, I'm not trying to use this more, is we can probe it by having an electron fly by, potentially through, but even just next to. And there is a reason to believe that we can extract quite a lot about the dynamics inside because of the following idea. That when electrons and holes are moving inside matter, typically on a picosecond time scale, by the way, because it's a typical scale we see for most of these dynamics in solids, they will accelerate and decelerate. So they inevitably create electromagnetic fields, near fields around them. And those near fields are ones we could potentially sense with an electron probe because we're very sensitive to the near fields. Right? That's exactly what we are kind of expert in doing. So what we develop is a microscope where we sense the near fields and then we reconstruct the dynamics inside. And we call this charge dynamic electron microscopy. And charge dynamics is what we're after, or CDEM. This is a major effort that we're doing with ICFO, this Javier Garcia de Abajo, and with EPFL, Fabricio Carbone. It's 2 experimental efforts that we were doing for 2.5 years. One led by Ivan Madan, he was a postdoc with Fabricio Carbone. And one by Michael Yanai, he's a PhD student in my lab. And there are 2 experiments that are being done, both shared by both groups. I'll describe them in short. The one in EPFL is looking into plasma dynamics, The idea is to take a piece of copper, bombard it with a laser pulse. There is a cloud of plasma that is then created around it. And then we ask whether we can repeat this experiment many, many times, bring the electron through, and each time collect the fields, reconstruct the plasma motion. And the analog experiment will be the one we have at Technion, is the one where we have electron hole dynamics in solids. We really like indium arsenide. It has very strong different mobility to the holes and the electrons. And by the different mobility, what we basically get is that we can expect the electrons to run away from the holes and then create a very big dipole inside and more complicated dynamics, hydrodynamic type. And those are the two things we were doing. And I'll show you a bit more on the experiment we were doing at Technion. But the type of data we get, that's the data. That's what the electron is sensing. Every pixel in this movie, that's a relatively simple geometry. But every pixel here is a set of experiments. Because what's happening here, that's the simplest geometry. There is an indium arsenide at the top, laser hitting it at the center. Then there will be some charge dynamics inside solid in there. If it recognizes my pointer, right? So inside there will be some charge dynamics, and it will cause terahertz fields nearby. And those terahertz fields will now cause the electrons to get accelerated or decelerated. So the red and blue is what happens to the electron in time, accelerated or decelerated. It's a function of time in different points. And one of the things you already see from this simple experiment is that the electron doesn't only get accelerated. You would expect, like, naively, electrons to get torn apart and then come back to the holes. So you'll expect one moment of some field. So the electrons will be, let's say, only decelerated briefly and then come back. But we actually see multiple oscillations of that. The fact that it oscillates multiple times tells you something that the hydrodynamic theory, at least I didn't expect it from the simple theory, because I expected the dipole to be created and to get annihilated, but instead we see something that looks like it oscillates. Right, that's already a point where experiment tells us something that the theory didn't really anticipate. Yeah.
Tell us more about the laser. How tightly is it focused? Is it a pulse?
It's a pulse in this case of about 50 femto and of about 50 micron size, or maybe 40 something micron size. So it's actually not focused very tightly. It's 800 nanometers, which is a condition known for in indium arsenide to create this type of dynamics. People call it photodember. The photodember is the name of electron holes being torn apart. Photodember means like by the light giving it a kick. Yeah.
It's because they don't understand precisely. So at what time is the laser hitting? Is it at 0? Or?
Yeah, what we call here 0 is the time. And you actually see a little bit of signal before 0. Yeah. And why is that? It's if you think about the electron, it passes a little bit before, but the laser is hitting and the field runs faster than the electron. So it could actually alter the electron even if it passes a little bit before right? The sample here is 60 microns thick. So the electron takes a while to pass by. That's one example of in this case, it's 70% the speed of light. So you can calculate in a fraction of a picosecond before you'll already get a signal.
So what this blue stuff I'm seeing, how do I interpret that? This is a shift in the probe electron's energy.
Yeah,
so
and I'll focus on one pixel to show a bit more, which will help you. But for a start, imagine the electron as a point for a moment, as a point charge,
right,
which what I kind of advocated against, but let's go for it. And in this case, the wavelength is larger. It's a terahertz field. So it actually is not a bad approximation for the electron to be almost a point charge. And then if the electron comes, the field oscillates. And if the electron comes at a time where the field points up, it will be decelerated, or well, depends what maybe accelerated because it's a negative charge. And when it points down, then it will be decelerated. So that's the game that you're basically playing, right? And the field has components that are not pointing up and down as well, but the electron is not sensitive to those. But if you have a dipole inside that is mostly pointing upward.
Energy shift to the laser.
Yeah. We can do with this many more interesting geometries. So here is a more interesting geometry, I would say, because there is now the laser is hitting the sample still from below, but now some of the field actually penetrates through it, and you see then the oscillations of the field on the other side of the triangle-shaped structure, right? And now we also shifted that to study the tip, because around the tip there is the strongest enhancement of the field, and you can play with this for quite a lot of different regimes. Yeah.
Polarization of light.
In this case, the experiment actually doesn't change. It's a function of polarization.
What is the
But we were doing different ones, but it's always, of course, perpendicular to the laser field. And for those ones, I don't remember, but we measured for both different polarizations and we saw the same movies. And the photodember is actually famous for not caring. But we did experiments not published yet, and I may have the data that we don't know how to interpret, where we take different materials where there is also rectification happening. Chi2 rectification will be very sensitive to polarization. And that one definitely cares. And the movies look different. And we don't know how to explain yet what's happening there. But that's a good question generally to think about.
10 more minutes. I just
Yeah,
wanna make sure
so-
that you kind of get through
Yeah, so I think I'll maybe then I'll stop with questions, so we're not at least for this, and we'll go back to discuss those things after. So I'll just say briefly that I promise you we'll look at charge dynamics. So what we basically, each pixel here is an entire experiment, and I'll not describe exactly how we get it because I think we'll not have time. I'll just say that the theory we apply with the full wave packet description for the electron will match pretty well. And the top will be experiments and the bottom theory. So I think we can reconstruct the field very accurately with this. And when doing that, we are reconstructing then what the charge dynamics will look like. So those are now maps that we reconstruct of the hydrodynamics inside. And the black and yellow will be the hole in electrons, the net charge inside. And what you find is that to explain the experiments, we need multiple oscillations of the charge. And I feel with this that this is an interesting thing because there are more oscillations there than I expected. And that means that the charge dynamics is much more advanced and complex. And it means either that the hydrodynamic model is not the right thing to apply, or that the actual physics is more oscillatory than we would expect. Either way, it's interesting. And I think it tells us something new. Anyway, we're thinking about other things we can study with that. You can wonder whether we can look at the dynamics of vortices in superconductors, for example, or think about other condensed matter systems where there will be some fast change and dynamics inside, and what we can see, what's the limit of that. And it's a long story. But I want to take a couple of minutes to kind of take you to another place, because so far we talked about quantum in the sense that the electron is a wave packet, but the light was always classical. And I want to say a couple of words about the opposite situation, because you can ask, what happens if we also think about a light as being quantum in interactions with electrons? So now both sides are going to be quantum. And I think there is important science to say about this. So first, the exploration of electron interactions with quantum light, it's fairly recent. The first theory to actually to do the theory for free electron interaction with quantum light, this is a single author PRL by Ofer Kfir. And this is from the Javier Garcia de Abajo groups. And this is all 2019 theory papers. My group was looking at the opposite situation of what happens when we create quantum light from the electron. And that on this, the first papers are even more recent on what's the nature of light coming out from an electron. Is it classical, what we call coherent state, or not necessarily? On experiment, this is all theory. On experiments, the first one, this is exactly a year ago from my lab. We looked at what happens for light interaction with electrons when the light is quantum, or at least carrying on classical statistics, even the first step. And that's measuring following the theory papers. And then on the experiments on what happens for the light emission, this is a science from a few months ago and science advances from last week, looking at coincidence. So it's still not the full thing, but they see coincidence between electron and photon emission. So you can say that's Fock state heralded by the electron, if you like. And actually there is still in review a paper from my group that was more that came before but takes forever in PRX, that is up to 3 photon emission from a single electron that we are showing that we can create and heralded by the electron measurement. And this is all on where we can measure things. But I think it's worth giving a couple of minutes to this very basic question of what's supposed to be the quantum nature of light coming from electrons. And the motivation for that, and I'll not jump deep into that, if I use super few slides, is people are now interested in creating quantum light. And there's always a big debate of whether those kinds of companies are really underdogs or just promising underdogs in quantum computing, but they're definitely not currently the leading efforts for quantum computing. The reason we don't see a lot of photonic quantum computing out there is mostly, and that's the bottleneck for all of those players, that the sources of quantum light are not good enough. And people here are working on better fidelity, better repetition rate of light sources that will have quantum properties. So I want to propose the free electrons as a candidate to create light quantum properties. And that's basically where I'm going with this. And I don't think I have much time, but that's an idea that was pushed by my students originally. And I think is really wonderful for why the electron wave packet shape allows us to treat electrons as kind of effective qubits. And once they interact and emit light into certain structures that we can design, those will actually have quantum properties to them. The measurement of the electron energy, which we use so far for microscopy, we can actually use that to do heralding on the electron and post-selection of specific light states. And that's part of the game. And we actually show that we can create very desirable quantum light states like multi-legged cat states and GKP states. And I'll not have much time to discuss this, but I will say that there is a long jump on this one, and why GKP are exciting things are worth an entire talk. But I want to ask, for people coming from electrons, radiation, right? Like back to this old stuff. Those are 4 examples of electron radiation experiments by us and by others. Electron radiation is famous for being very broadband. You can do this in many, many areas of the electromagnetic spectrum, but it's always described, and we did this for years, as classical. We solved Maxwell's equations for the radiation coming from electrons. And it's not so obvious to me now that it's actually true. Because we think about this for many, many years, and maybe one thing to remember from the talk, and this is a review we're writing with MIT that's coming out for you soon, is that the light state coming from electrons is not necessarily just classical, and it's not always correct to consider light radiation as classical. The paper to remember for this, the first to touch this, is by Aviv Korniali, is my student that's going to work with Shenhui Fan for a postdoc. The thing we realize here is that if you think about what's the quantum state of light coming from an electron, it won't necessarily be just classical, what we call coherent state, but it actually gets entangled with the electron radiating it. And that idea that the light created by the electron, even if flying very far away, is still entangled with the electron, is something that we understood is allowing you to say something. For example, you can characterize the electron by measuring the light if you do quantum optical measurements. And the entire field of quantum optics, for me now, is a playground to try to apply on free electron radiation. So that's something to remember, that electron radiation is entangled with the electron, and that allows us to do interesting things. So the final step in this chain, and that's I won't discuss exactly why we can do that, but that's the idea that goes to desirable quantum states, is that my students proposed this idea that how we actually specifically need to shape the electron now, so it won't just be entangled, but it will be entangled in a useful way. And an interesting approach to that is to create those, we call those electron comps. So those are electrons that are superposition of energy levels, with the difference between the electron energies being twice the photon energy. And we know how to design those. And now the idea is that we'll be emitting radiation at 1 photon energy, and then by post-selecting on the electron energy, we'll be able to tell not exactly how many photons were emitted, but we'll be able to tell the parity of the number of photons that got emitted, right? The parity, if it's odd or even. And apparently that kind of approach, really simple approach, already is allowing you to have radiation with cat state in its nature. You can show that it's a natural outcome of the electron. And then you can generalize that approach, and instead of working modulo 2, work modulo 4, and then you can get multi-legged cat states as well, which are important for error corrections. And what's even more beautiful is by stepping on this approach multiple times. So bringing out multiple electrons into the interaction point, what you will get is not a cat state, but what people call a grid state. And grid states, their Wigner function looks something like this, like those creatures. Those are states that are most famously known now as GKP states, or Gottesman, Kitayel, Preskill, are the ones that are today the most famous for error corrections in continuous variable quantum computing. And it's I think it's a beautiful thing that the electron interaction creates them in a natural way. It wasn't so obvious to me that there normally people work pretty hard to make that, and there is currently no experiment in the optical regime that actually did it yet. We are working on that, but the fact that the most desirable photonic states for quantum error correction is actually the natural result of multiple electron interaction is wonder to me. And you can actually choose the language of quantum information. You can show that the electron interaction with light is a stabilizer for the GKP state. So if you already created a GKP state, you can even apply electron interaction to fix errors. So the electron can act as a gate. The fact that that is happening naturally for the interaction between electron and light, I don't know. I feel like there is magic in this almost. It's a beautiful thing that the electron exactly creates that. And that makes this a pretty interesting and promising approach, but it's a long discussion for what's the best strategy and how far this and how much it compares with other methods. Since I'll need to finish, I'll just say one slide on this, and that's the actual experiments toward it. This is an order of magnitude, if not two, harder than anything I showed you experimentally so far. So don't consider this as a promising candidate for quantum computing yet. But I think that the steps towards it are really exciting. So I'll finish with this slide that if what we need to do, if we want to get to quantum light made of electrons, we need to solve several important challenges. One is the creation of electron clumps, those electrons that are superposition states. Another is to create the right photonic cavities and also have high efficiency interactions with them. And the last is to do coincidence measurements for heralding. And those, if we solve those four problems and know how to put them together, we'll get somewhere really interesting. And interestingly, all of those are being now addressed by different groups. So comms, we had this experiment, which was the first demonstrated comm, and now there is this theory paper showing how to optimize the comm to what we need by the Ropers group. For high Q cavities, we were competing for a while with the Ropers and Kippenberg groups and had several high quality cavity interactions demonstrated in recent years. For high efficiency, this is a paper going to come up in Nature very soon with MIT, where we showed the most efficient electron radiation from a structure that uses photonic flat bands. And this is still in review from my lab, where we showed few photon emission per electron, which is currently the experimental record for efficiency. And for coincidence, this is by other groups that showed the first coincidence measurements, and that's also done just in last summer, all out recently. And I think that all of those pieces are happening for many different reasons and are coming together, and that's beautiful. So this is becoming really exciting on both theory and experiments. And I think I'll stop with it here, so we have a little bit of time for questions. And thank you very much for coming.
One question about when these combs were first observed. You know, you're probably familiar with the upper threshold ionization experiments from the mid-'80s.
Yes.
Where electrons that are liberated by a high field then absorb individual photons, and the spectra are
right. And those are also considered a single electron per comb. So maybe I should present it differently. The reason I call this first is that here the electrons are relativistic and are in the right conditions for what I need. But the ATI, or above threshold ionization, was the predecessor of high harmonic generation as well. This was emitted from atoms, multiple peaks, and then leading on later to the understanding that this will also mean that you will get high harmonics created from those electrons. So what we have here is even in the first experiment, this was the nature physics, we had more than 1,000 peaks. So we got more than any ATI shown so far. And the conditions are different because it's relativistic. But you're right, the comps themselves.
Quantum, per photon absorption. Yeah. The basic physics.
Yes, the basic physics is the same. It's just not relativistic there. And this should be the first comp to present. And if we may find a way that the non-relativistic electron will allow us to do the same, that will be even better. Yes.
Can I get another question about your vertices in the 2D materials? So, am I understanding correctly that you measured basically nulls in the field, but you inferred the phase? The phase was not measured; it was simulated basically. I see. And then in the shot by shot imaging, these were, I guess, they were repeated experiments at slightly different delays.
Yeah.
So the apparent motion of these vortices, how much is that attributed to simply shot-to-shot variation in the
Hmm.
imaging. And
So
then when you see something
yeah.
that's annihilating, could it simply be that, it's not like these things are moving and annihilating, they're just on a frame, they're just not there anymore.
Yeah, so it's a matter of stability. No, so this is real. It's not, because basically even a single frame here that we do is, remember that every frame we have per pulse about 1 electron, actually sometimes below, which means that electron, when it will come to create an image, it will not create a full image of that frame, one frame. It will create one hit on the detector. To make it collapses on one location on the detector. What we actually do is repeat it many, many times. Our repetition rate is 1 megahertz, a million frames per second, which means we get about 100,000 or a little bit more of electron hits per second. What we actually do is integrate for minutes for one frame. So if that thing is not repeatable, if the dynamics of vortices was not exactly the same for each pulse hitting it, we would get just nothing. It will smooth out. So we are lucky that the experiment here is repeatable. So we can do stroboscopy kind of measurements. That wouldn't be possible otherwise. So for example, if you think about plasma dynamics, which is known to be very chaotic in its dynamics, we actually don't see everything with such nice features because it's not as repetitive. Well, the hydrodynamics we saw was actually pretty repetitive, but everything that's not exactly repetitive, we will not be able to see with this method.
And just to stop, I'll bother you no more after this. So the electric field that you are sampling with the electrons is it's the fields inside the material, it's the phonon, it's some kind of charge separation fields, or there are electrostatic fields in the material. Is that what's being sampled?
The field we're studying
in the some kind of a mode in the material.
Yeah. So if we think about
what it actually is, the field.
Yeah, what happens to the field that it excites? If you can think about it like a waveguide, right? The light in a waveguide gets coupled in and then propagates inside. But in those more fancy materials, like 2D materials, it doesn't couple to just a field that jumps inside a waveguide, but into some other excitations, other things. But it's still guided inside. So it is in the end an electric field that is inside there. It just ties very strongly in this case to phonon dynamics. So it's a hybrid with the phonon dynamics. But what we see is not the phonons, but the electric field part of this hybrid creature.
And do you know the dispersion relation to that field for the material?
Yeah, we can actually extract it from looking at the dynamics, but it's also known pretty well by now by different experiments. And we saw that it fitted very well.
Okay, okay, Sergey, quick, a very good
Last question.
So you had said that you wanted to generate 1 electron per pulse most of the time. And would the picture change with many electrons generated at the same time? At which is there anything which that we can learn from conditioning on those detections when you have, let's say, 5 or more, 10 or more?
Yeah, so it's always a game for us. The more UV pulse we put in, more UV energy, the more electrons we pull out. At some point, more electrons repel one another. It's an annoying thing about electrons imaging. They repel one another, so it reduces the quality of the image, both in the resolution in energy, because their energy spread grows, and the resolution in space. So we work at 1 electron per pulse because to get the best resolution. But if we want to image something with resolution that's not as good, we can actually increase. So that's the game. It's always the game. And what happens to the multi-electron pulse? There are many questions, like what's the quantum relation between 5 electrons in 1 pulse? There are 2 archive papers from a few weeks ago that are looking for pairs of electrons and showing correlations between them. So even the assumption that electrons collapse one another and maybe have independent nature, it's probably going to be shown wrong in coming years. Because there is G2 type experiments on 2 pairs of electrons. It's recent from 2 weeks ago, 2 papers back to back, Homeloff and Wapos. So check it out. I think this is going to be fun to start asking what's actually the quantum nature of many electrons per pulse. So.
Excitement. Thank you very much for giving.
Thank you. And we'll make sure you don't forget your